Welcome to my channel. I'm Ignatius, a student of Ghana Communication Technology University. We are here to talk about two things, which are the impact of the data. So firstly, we would like to talk about the impact of the data path cycle on CPU performance. So we have to know what the data path cycle refers to. This refers to how data flows through the CPU, including the registers, memory, and execution unit. We will also talk about the key components of the data path. We have the instruction fetch unit, which retrieves instructions from memory, the register files that store small, fast access data for operations. We have the arithmetic logic unit, ALU, which performs calculation and logic operations. Memory access unit, which reads and writes data to or from main memory or caches. Control unit, which direct the flow of data and operation. Now let's move on to the impact. So the first impact is the propagation delays. Now, every component in the data path takes time to process data. Longer delays means slower overall processing. For example, if the arithmetic logic unit takes long to compute, subsequent operations must wait. So we also have the pipelining stores. Modern CPUs split tasks into stages, which are fetch, decode, execute, etc., enabling multiple instructions to be processed at once. If a stage is delayed, example, waiting for data to arrive from memory, the pipeline stalls, slowing down the entire process. We also have the memory bottlenecks. Accessing main memory is significantly slower than accessing registers or cache. If the CPU frequently needs data from memory due to inefficient caching, performance drops drastically. And then finally, we have power and thermal issues. Complex data paths consume more power and generate heat. This can lead to thermal throttling, where the CPU slows itself to avoid overheating. So now I want to talk about the second thing for today, which is how does the CPU fetch, decode, and execute instructions. Yeah. So the fetch, decode, execute cycle, known as the instruction cycle, is a step-by-step process that a CPU uses to carry out instructions from a program. Each stage involves specific operations. We'd like to talk about the first stage, which is fetch stage. This is the step where the CPU retrieves the instructions from memory. We have the program counter, we have the instruction fetch. Let's talk about the program counter. The program counter holds the memory address of the next instruction. For example, if the PC value is 100, the CPU will fetch the instruction stored at memory address 100. So the instruction fetch, the address in the PC is sent to the memory through the address bus. The memory sends the instruction back to the CPU via the data bus. This instruction is stored in the instruction register, which is IR. We'll be seeing the IR more often, so we need to get a closer look at it, which is the instruction register. So we are moving on to the decode stage. Here the CPU interprets the instruction fetched in the previous step. The instruction decoder, the binary data in the IR, is analyzed to determine what operation to perform. Yeah. For example, if the instruction add R1, R2, R3, the CPU decodes it as add the content of register R2 and R3 and store the result in R1. You have the operand identification. The operand identifies the CPU actually identifies the source and destination operands. This could be registers, example R1, R2, and memory addresses, example 0x200, yeah, or 0x200. If data needs to be fetched from memory, the address is calculated at this stage. We also have the control signal generation. The CPU generates control signals to activate the required component. Example, the ALU for addition or memory unit for data access. Continue. Now move on to the next slide here. So we have the final one, which is the execute stage. So the CPU carries out the instruction. This stage varies depending on the type of instruction. Arithmetic slash logic instructions. The ALU performs the specified operation. Example, addition, subtraction, bitwise, and slash all. Example, If the instruction is add R1, R2, R3, the ALU adds the values of R and then give the result in R1. Yeah, so now we talk about memory instructions. If the instruction involves memory, example load or store, load, the CPU fetches data from the memory address into a register, and the store, the CPU writes data from a register into the memory address. We also have the branch instructions. If the instruction is a conditional jump, example, if A is greater than B, go to X, the CPU evaluates the condition. If the condition is true, the PC is updated with the new address X. Otherwise, the next sequential instruction is executed. So, we also like to talk about how modern CPUs optimize the cycle. Modern CPUs use techniques like pipelining, superscalar architecture, speculative execution, out of order execution. Let's start by talking about the pipelining. Multiple instructions are executed simultaneously in different stages. While one instruction is being decoded, another one can be fetched. And talking about the superscalar architecture, multiple instructions can be executed in parallel if they are independent. Yeah. And the speculative execution, the CPU guesses the outcome of branch instructions to avoid waiting, executing instructions ahead of time. Out of order execution. Instructions are executed in a non-sequential order based on data availability and dependencies. Example of the cycle. Consider this assembly instruction. Fetch. So we are going to fetch, and the fetch, this is the CPU fetches the instruction add add R1, R2, R3 from memory. The instruction is stored in the IR. Yeah. So decode. The CPU decodes the instruction to understand. Operation. The operation there is add. So add is what? Addition. And the operands, read values from R2 and R3, read the results, write the result to R1. Execute, the ALU adds the values in R2 and R3, then the result is stored in R1. Yeah. So uh, let's take these two numbers for example. Two numbers 5 and 3 are stored in memory addresses 0x100 and 0x104 respectively. The program needs to load the two numbers into the CPU, add them, check if the result is greater than 7. If true, store the result in another memory location called the 0 times 108. Yeah. So assembly. So this is practically how uh, everything works. So the first one you can see load R1 0 times 100. Load the value at memory address 0x100 into register 1. Yeah. And the same thing load R2 0x104. Load the value at memory address 0x104 into register 2. Register R2. It goes on like that. Then we come to where it compares the values. It compares the values. Compare the value in R3 with 7. So after adding, we are comparing. We are comparing if it's what is 7. First of all, after loading the two numbers, we add R3, R1, R2. Add the values in R1 and R2. Store the result in what? R3. So that is R3. So let's start from the beginning. R1 means load the first number, R2 you load the second, and the R3 is another register to store the result of adding both numbers. Then the next step, you compare whether the number is equal to 7, yeah, or greater than 7. So if R3 is greater than 7, branch to instruction at 0x200. Store R3 0x108 and it store the value in R3 into memory address 0 times 108. Yeah. So this execution, a more detailed explanation of what happened in the previous slide. So execution of the fetch decode execute cycle. Instruction 1, load R1, which is a 0x100. So we fetch the CPU fetches the instruction load R1, which is 0x100 from memory. The instruction is placed in the instruction register, which is the IR. So it moves on to decode. The CPU decodes the instruction. It identifies the load operation, the target register R1, and the memory address 0x100. Now it moves on to execute. So the memory unit retrieves the value 5 from address 0x100. The value is stored in R1. Yeah, now let's move on to the second one. So instruction 2, it says what? Load R2, which is the address is 0x104. So first of all, it fetches. So the CPU fetches the instruction load R2 0x104. Now it moves on to decode, same process as the first one. So it moves on to decode. The CPU decodes the instruction. It identifies the load operation, the target register R2, and the memory address 0x104. Then now it executes. After decoding, it executes. The memory unit retrieves the value 3 from the address 0x104. The value is stored in R2. Yes. So now the instruction 3 is what? Add R3, R1, R2. So this is where the addition happens. This is where the addition happens. So the CPU fetches the instruction add R3, R1, R2. So it decodes. The CPU decodes the instruction. It identifies the add operation. I told you earlier on that this is where the addition occurs. So it identifies the add operation and the source registers R1 and R2. Now it executes. The ALU adds the values in R1 and R2. It adds the value in R1 and R2, resulting in 8. The result 8 is now stored in R3. R3. Yeah. Instruction 4. Yeah. We are about to compare. We are about to compare to see if our result is greater than 7. Yeah, it's greater than 7. So now we fetch. The CP fetches the instruction compare R3. CMP R3, which is 7. No, sorry about compare R3 7. So it's comparing R3 and the 7. It's comparing R3 and the 7. So now it decodes. The CPU decodes the instruction. It identifies the CMP compare operation, the register R3, and the immediate value 7. So I told you guys this is where the comparison occurs. So now it executes. The CPU compares the value in R3, which is 8, with 7. It sets a status flag indicating that 8 is greater than 7. Now let's move on to instruction 5, which is BGT 0 times 2 0x200 or 0x200 fetch. Now it fetches. The CPU fetches the instruction BGT or branch if greater than. That is the meaning, branch if greater than. So the fetches the instruction branch if greater at what? The address 0x200 at that address. Now it starts to decode. The CPU decodes the instruction. It identify the BGT into bracket branch if greater than operation and the target address 0 times 0x200. I don't know why I like saying times, but 0x200. Now it executes. Since the comparison result is true, which is R3 greater than R7, the CPU updates the program counter, which is the PC, to 0x200, skipping the next instruction. Understand? So the instruction 6, which is instruction 6, store R3. Store. So we are now coming to store. We are about to store. Yeah. We are skipping it. We are supposed to store, but we are skipping a course. What the 8, we got R3 to be greater than what? The 7. So this instruction is skip because the branch condition was met in the previous step. Yeah, that's what I was trying to say. Sorry for the fumbling. But that's what I was trying to say. Because the R3, which we got as 8, was greater than 7, the branch condition was met. So this step, which should be the store, which should be the store, was skipped. Yeah. So now we have the pipeline optimization. In the body CPU with pipelining, while load R2 0x104 is being fetched, load R1 0x100 is being executed. This overlaps speeds and the program execution.